Hi. So in this video I'm going to talk to you about the hyperbola. Okay? Just take a look at that. Isn't that fantastic? I love seeing these. Maybe you don't because of the pollution and so on, but the actual shape just really fascinates me. If you have a look at the actual graph of a hyperbola, there are two branches to it, both here and here, symmetrical about the y-axis. And if you rotate the whole of this shape, the whole curve, around the y-axis, 2 pi radians, 360 degrees, you end up with what's called a hyperboloid. And that is the shape that these wonderful buildings here make. I actually took that photograph myself. That comes from Nottingham, just in case you are wondering. So I'm going to be talking to you about the hyperbola today. Stay tuned. Try and hang it out for as long as possible. Okay? You should enjoy it. There should be something for everyone in this. So, this is the curve of the hyperbola. Notice the two branches on either side, symmetrical about the y-axis. Notice also this curve has got asymptotes. What's all that about? Well, before we describe what the asymptotes are and why they are as they are, let's have a look at the Cartesian equation. X squared over a squared subtract y squared over b squared equals 1. Why did I emphasise subtract? Well, if you've seen the equation of the ellipse, you should remember that it's the same as this but plus. Okay, so that's the main difference between the ellipse and the hyperbola. The hyperbola in terms of the Cartesian equation. You've got plus for the ellipse, subtract for the hyperbola. So it's a handy way of remembering it. Now back to those asymptotes. Normally you're looking to see what happens when x tends towards infinity or y tends towards infinity to see whether there are any asymptotes. It helps us to see what the function is doing, what the behaviour of the function is as x and y get very, very large. In this equation here, if you let x and y tend towards infinity, then we can ignore the 1. When I say ignore, we're going to say that the right-hand side is 0 because when you deal with infinity, 1 is insignificantly small, of course. So when you say the right-hand side is 0, you can effectively write this. X squared over a squared equals y squared over b squared. Okay? And then I'm just going to rearrange it, make y squared the subject. So put the b squared over there. So you have b squared over a squared times by x squared. Can you see what we're going to do next? Square root both sides, and when you square root both sides, you'll have y equals positive or negative b over ax. Hence, y equals negative b over ax, y equals positive b over ax. That is how the curve functions. That's how the curve behaves as x and y tends towards infinity. So the asymptotes there are quite useful in being able to help us to draw the curve. So this curve is going to tend towards that asymptote, which I find quite fascinating in terms of the graphology of all of this. Is graphology a word? I don't know. Did I just make that up? I don't know either. Post a comment. Right, in terms of the parametric equations, there are these. X equals a sec theta, y equals b tan theta, or a cos theta, b sine theta. These are hyperbolic functions, sine and cos, hyperbolic functions of cosine and sine. Shouldn't surprise you then that they are heavily linked to what we're talking about now, the hyperbola. Now, how do these parametric equations work in terms of converting to Cartesian? Well, I'm going to show you, I'm going to demonstrate to you that they both work. Do you ever find yourselves wondering about the trigonometric identities and which one is which and how to remember them? Well, here we go. If I set it up as an identity, you should be aware of that one. Sine squared theta plus cos squared theta equals 1. I'm going to come by here because it's just, I'm right-handed and it's easier. If you divide both sides by sine squared, you get 1 plus cosec squared. Sorry, start again. 1 plus cot squared theta equals cosec squared theta. If you divide both sides by cosine squared theta, you get tan squared theta plus 1 equals sec squared theta. A handy way of trying to get those trigonometric identities. Now, because mine is involving tan and sec, I'm going to divide both sides by cosine squared theta to get the identity I want. Tan squared theta plus 1 equals sec squared theta. And then what I'm going to do is I'm going to substitute each one of those into these. So x over a is sec theta. So that's going to be x squared over a squared on the right hand side. The 1 is there. And y over b is tan theta. So y squared over b squared plus. Can you see how this can be rearranged to get that one there? Okay, I hope so. Just put that onto that side. You've got x squared over a squared minus y squared over b squared equals 1. Okay? So a rather simple explanation of how the parametric equations work there. What about the other ones? So here I'm going to use the identity cos squared theta minus sine squared theta is the same as 1. Remember that from Osborne's rule? Osborne's rule is effectively when you've got a product of sines or an implied product of sines, as in sine squared, then you make that term -1, so that would be -1 plus for the hyperbolic functions, okay? Hence cos squared minus sine squared is 1. Then when I put these in, so cos theta is x over a, so that would be x squared over a squared, and then sine theta is y over b, so that would be y squared over b squared equals 1. I'm going to write equals because it's an equation on the curve. And that is it. Even quicker to get the Cartesian equations from the hyperbolic form. Just another one of those small reasons why I prefer hyperbolic functions, if I'm honest, to trigonometric functions. Don't get me wrong, trigonometry is a blast. I love trigonometry, but hyperbolic functions just edges it for me. Anyway, I'm not talking about that. I'll be going off on a tangent, okay? Now, in terms of the A0 and negative A0, the x-axis crossing points, that should be easy to work out, shouldn't it? Okay. So when y is 0, obviously you've got x is positive or negative a. Okay. And clearly, well, I hope clearly, there is no y-intercept because you can't have y squared is equal to negative b squared. Okay. So no y-intercept. Okay? So for the moment, that's the basics of the hyperbola. Okay. Hope you found that useful. So a bit more detail about the hyperbola coming up. Well, a lot more detail. This is where, for some, it starts getting a little bit too complicated. So I put in the focus points here. You'll notice, like the ellipse, there's 2 of them, and for every focus point, there is a directrix. Now, just as in the ellipse, the focus point is a is 0, negative a is 0. It's symmetrical about the y-axis, and the equation of the directrix is x equals a over e, or x equals negative a over e. And here you've got the handy relationship between A, B and E, which I think I'll explain in a different part of this. Okay. I'm just going to mention about the eccentricity though, because that's quite important. If you haven't seen the video on the ellipse, watch that as well, because I'll talk about the eccentricity and what it actually is. But really it's defined by this relationship here, this ratio, PS over PM, where I'm hoping my diagram makes it clear what I mean by PS and PM. So PS is the distance between this point here and the focus, and PM is the distance between this point here and the directrix. Now, P can lie anywhere on the curve. Okay? I've chosen this branch of the curve here. I've chosen it up here because I generally prefer things in the top right quadrant because everything's positive. Keeps things simpler. So we're talking about the relationship between any point on the curve, the hyperbola, any point there, the distance between that point and the focus, and the distance between that point and the directrix, that is related by this relationship between E. And it's the same with the focus directrix property of the parabola and also on the ellipse as well. Now in this case, the relationship is that PS over PM gives you a number that is greater than 1. I'm hoping you can see that's obvious. Well, a bit less so maybe, but it should be the case that PS is always greater than PM. Maybe if you took a point on the extreme of the branch, when it's much higher up, it kind of looks a bit more obvious, doesn't it, that PS is going to be larger than PM. Okay, and that gives us the result that E is greater than 1. Okay, E is greater than 1. Yeah, which is something that you need to be aware of as well, except for when E tends towards infinity. When we use greater than signs, we're effectively using actual values, numbers. Okay, infinity is not a number; it's more of a concept when something tends towards a very large value. Okay, but I'm just going to say that when E is infinity or tends towards infinity, you've actually got a straight line, which I think kind of makes sense to you. Okay, I don't think there's anything else I need to talk about. No, so that's it for this segment, I think. Now then, I'm going to talk to you about this, where that comes from. If you've seen my video on the ellipse, then great, because pretty much all the work was done in that video. If you've not seen the video, why don't you watch it? Okay, because I'm going to do the similar sort of things to what I did on that video. I've set it up in the same way. That is, I'm only really interested in this part of the hyperbola, so I'm going to ignore the rest of it so I can fit everything on my screen. Okay, and I'm going to try and prove the result in terms of A, B and E. I want a relationship, I want a formula between A, E and B. And we're going to do it using this principle here. Okay, we're going to have a starting point. The starting point is E is defined to be PS over PM. Now if you remember from the other video I showed you, what we do is we first will write it like this, okay, square both sides, rearrange PS squared equals E squared PM squared, and then we use Pythagoras' theorem to work out what the distance PS squared actually is. That's our starting point, and you notice exactly the same thing. You'll get very similar results. In fact, you'll get exactly the same results right up until the very end, okay? But in case you've not seen it, here it is. By Pythagoras' theorem, that hypotenuse is that squared plus that squared. So y squared, the y coordinate squared, and then difference between the x coordinates is going to be AE subtract x or x subtract AE. Doesn't really matter which one you use. And then expand the brackets as such. And then for PM squared is going to be just this horizontal line there. So difference in x coordinates, x subtract every, there we go, or every subtract x squared. And then, because we're interested in this result here, E squared multiplied by PM squared, E squared multiplied by this, expand the brackets, we get that. Okay, if that was a bit too quick for you, just replay the video. Okay, and then we're going to use the result. Okay, we're going to use the result that these two are equal. In other words, we're going to set that part there equal to that part there. And as with before, exactly the same as before, those two terms are going to cancel because they're exactly the same. And because I've now got space to write this new bit on, there it is, that's what we've got. So this bit is the same as this bit, there we go. Rearrange it a little bit. X squared on one side, factorise. A squared on the other side, factorise. Where is this heading? Well, I want to get some sort of formula looking like that, okay, which is why I'm going to try and rearrange it to look like that. As with before, with the ellipse, when we divide by 1 minus e squared, we get this result here. And then, because it's a hyperbola, what's the difference? Okay, so far the working is exactly the same as the ellipse, but what's the difference? Do you know what it is? It is that, isn't it? It's e is greater than 1. Okay, it's e is greater than 1. Because you can see here, when e is greater than 1, this bit here is going to be negative. So what we're going to do is, we're going to multiply top and bottom of this fraction by -1. First of all, to get it in that form there. Okay, so doing that, let's just get rid of this. Doing that, we're going to get negative y squared over a squared e squared minus 1, all writing like this. That way it gives us something in that form. But the reason we're doing that is because e is always greater than 1. Even this new form, when you check, e has got to be greater than 1, so this bit here, the sign doesn't change. If you substitute a value of e between 0 and 1, okay, that bit there is going to be negative, you go back to the ellipse. So algebraically, that's why this is for the hyperbola and e's between 0 and 1 is for the ellipse. Okay, remember e equals 1. Doesn't make any sense there. I kind of mentioned it briefly, okay, but doesn't really make any sense there, does it, in terms of putting e equals 1, because you get infinity. Obviously the equation is completely different. Y squared equals 4ax. There's no x squared term. So all I'd say is that e equals 1 just simply does not apply here. And even so, with the parabola, we're not actually getting a relationship between a, b and e, to be honest, because e is always 1. Okay, e is always going to be 1. And the reason, of course, is because here, sorry, not the reason for e equals 1, the reason that b squared equals a squared e squared minus 1 is because this denominator, b squared, has got to match that there. So I'm hoping that makes sense to you as to why you got this rather important result. Remember, when you've got an equation given to you, it might be the case that in Cartesian form, you've got what a is and what b is. You can actually use that rather handy result to calculate the value of e. Why do you want to do that? Well, going back to the graph again, remember, each focus point is in terms of e. Each directrix is in terms of e. In terms of getting the shape drawn, okay, you need to know what that focus point is and what that directrix is. Okay, I'm hoping you found it useful. Nothing new in this bit, I just wanted to show you this. It's quite amazing, it's fantastic, okay? A gift that I found somewhere in terms of what the hyperboloid looks like when you rotate the hyperbola around the y-axis, okay? It looks amazing. I could look at that for well, many minutes, say, not many hours, because I'll then probably tune out and go and do something else, okay? But it is quite stunning, I think. I hope you enjoy it as well. So there you have it. All you need to know, possibly, about the hyperbola. I hope you found this video useful. I hope you found it interesting. Okay? I'll see you again.